Welcome to our lab report on friction and kinetic energy by Ryan Farragon,
Kate Hammond,
and Nick Kirchenberger.
So our main research question was, how does an increase in the friction force exerted by a surface affect the kinetic energy of the system? And our hypothesis was that if you increase the friction force generated by a surface, it's going to decrease the kinetic energy of the system because of an increase in non-conservative energy, in this case in the form of friction, allowing most of the energy in the system to leave as heat. And the main findings of the experiment was that as the frictional force exerted by the surface will increase, the kinetic energy of the system will also linearly increase because work will be negative.
So for modeling this, we have our system schema on the left and our free body diagram on the right. Components is the IOLab, our string, the weight in the pulley system, and then the earth at the surface. And our forces were frictional force, applied force, tension and gravity forces, and force normal. Okay, so for modeling friction, frictional force always counteracts the force that's pushing on an object, so the applied force. If kinetic energy decreases, frictional energy increases, and as frictional force decreases, kinetic energy can increase. But an object will not move if the applied force is not greater than the static frictional force. And so basically with Newton's second law, force normal is equal to mass times gravity. If you have the greater mass, the greater force it's going to be experiencing, and you're going to need a greater applied force to do the same amount of work as you would with an object with less mass.
The experimental design included the IOLab wheel side down, being dragged with a constant force over dirt, 60 grade sandpaper, and a scarf that was folded over once. We used the IOLab after calibration to measure force, position, and velocity, and we recorded the weight of the IOLab and the weight that was being used to pull the IOLab at a constant force. We calculated the kinetic energy of the systems and the frictional force for each system exerted. Possible flaws were poor calibration and lack of re-zeroing between trials. We had to redo several trials due to this issue, so that could make the force exerted unproportional between surfaces. These were the recorded graphs and values that the IOLab tracked over each surface. The first figure is for dirt, and the second for sandpaper, the third for scarf. And these are their respective forces required to overcome static friction and to maintain motion over kinetic friction with their final and initial velocities. These are the calculated values for the frictional force and change in kinetic energy for each surface. We saw that as the frictional force exerted by the surface increases, the change in kinetic energy of the surface system also decreases. Even though our graph is in absolute values, the change in kinetic energy is negative, meaning the work is negative and energy is leaving the system due to an increase in friction.
These are the equations we use to measure changing kinetic energy, the frictional force, and the force applied to ensure that each trial remained constant.
So in terms of scientific reasoning, frictional force and applied force are inversely proportional to each other, and so frictional force is always going to oppose applied force. Kinetic and static friction are both acting on this object. The resistive force will eventually become kinetic frictional force while the object is in motion. And because the friction force is not a conservative force, the work done is not capable of being stored in the system as potential energy, and so that work energy is transformed into thermal energy of the IOLab system. And so the thermal energy will flow through the surface and IOLab, and that comes to the law of conservation of energy, which states that energy cannot be created nor destroyed, but it can be transformed.